Hello everyone, welcome back to 3 Deviations. In today's video, we are going to be talking about some more indefinite integration. So yesterday we really covered the integration table. So the integration table was a nice table that we could use where we put the function on one side and we put its antiderivative or formula to receive its antiderivative on the other side. So an example is if I had cosine of x, the other side would be sine of x plus c. And we did that for all of the different derivatives and antiderivatives, and I hope you have those memorized by now because we're going to be using those. What really is the strategy for today is using those formulas in the table and manipulating our integrand, or the function inside of our integral, so that we can use the table. So right now, the table is the only thing that we can use to integrate. If it's not on the table, we cannot integrate it. So we need to manipulate it so it is something that is on the table. Let's try an example here. So let's take the integral of 2x squared plus 3 cosine x dx. So first what we're going to do is we're going to apply the sum rule so we can separate them. We're also going to take the constant out. So now we have 2x squared, and then we have cosine of x. All right, so now to find the antiderivative, the indefinite integral of 2x squared, well, we add 1 to the power and then we divide it by the new power. So that becomes, so we get x cubed, and then we have 2/3. So we get 2/3 x cubed. Then cosine of x, we just said that that goes to sine of x. Great. So now we can plug that in. We get 2/3 x cubed plus 3 sine x plus c. Of course, we need to add that plus c. That's always important, just to make sure that this is a family of curves that could have any y-intercept, since the derivative kills the constant term. All right, so now we can move on to another example. So why don't we try taking a slightly more challenging integral of 2x cubed minus 6x plus 3 over x squared plus 1 dx. All right, so again, we need to manipulate this so that we can use the table. So this guy looks fine. This guy looks fine. Those are just monomials. This guy, though, we're going to have a little bit of trouble with. All right, so let's deal with this. So we have 2x cubed. We have 6x, negative 6x. Then we have 3 over x squared plus 1. All right. So now we're going to separate all of this with the sum rule. So we get the integral of 3 times, 2, should be a 2 there, 2 times x cubed dx minus the integral of 6x dx plus 3. We can take out the 3 times the integral of 1 over x squared plus 1 dx. All right, so 2x cubed, that's an easy one. This one goes to x to the 4th, then 2 over 4, so we get 1/2 x to the 4th. 6x, negative 6x, we get negative, then we have x squared, then we have here, so then here we're going to have 6 over 2, which is 3. So we have negative 3x squared. Now this guy, what we need to do, we take out the 3 goes there, that gives us 1 over x squared plus 1. Well, that's in the table, that's the arctangent. So now we have the 3 times the tangent inverse of x. All right, so now we can plug this into our final solution. So we're going to get 1/2 x fourth minus 3x squared plus 3 inverse tangent of x plus c. All right, so that is our final answer for the second example. As you can see, it's pretty easy as long as we know how to do that manipulation, get our constants out, make it so that our integrands look like something that we can deal with in the table. All right, let's do a word problem. So in differentiation in Unit 2, we were talking about how in kinematics there was a nice relationship between position, velocity, and acceleration. That if I differentiate here, I get velocity, and then if I differentiate here, I get acceleration. Well, we can do the same with integration. We can go back and forth between velocity, position, and acceleration using integration and differentiation. So here we have differentiation, here we have integration, so we can use integration to go back. So in particular, we can use integration between velocity and position to find our displacement. So let's say that we have a particle position function, or particle velocity function, sorry, of negative t squared plus 6t plus 6. All right, so now what we can do is we're going to find the displacement on the interval between 1 and 4. So to do this, we are going to take the integral between 1 and 4 of negative t squared plus 6t plus 6 with respect to t. So we have negative t squared, we have 6t, we have 6. Negative t squared goes to negative 1/3 t cubed. 6t goes to 6 over 2 t squared. And then 6 goes to 6t. So those are really easy indefinite integrals that we can take there for antiderivative. Now we can plug in our antiderivative values. So we get negative 1/3 t cubed plus 3t squared plus 6t. Then we evaluate that between 1 and 4. So this is the fundamental theorem of calculus part 2. We're evaluating our antiderivatives between our endpoints, between our bounds of integration. So when we do all of that math out, we're going to get negative 42, or we're going to get 42 here, and that is going to be our total displacement traveled along our parabola, which is going to look something like this. And it's going to find our distance between 1 and 4. So that is how our integration works and how our indefinite integration works. Now we can apply that to definite integration like we did in this word problem. All right, so in the next video, we are going to be moving on to our final topic in what is considered Calculus 1. So our final topic is going to be probably the most universal rule for integration called the substitution rule. Of course, in Unit 6, when we're in Calculus 2, we are going to be moving on to more advanced techniques. But for now, our main goal for the rest of Unit 4 is to build up our strategy for elementary anti-differentiation so that we can use it to apply it to different scenarios in Unit 5, where we will begin Calculus 2. All right, thank you for watching, and we will see you in the next one to talk about the substitution rule.